Hello, everyone. Mike Muller here again from Rutgers University. Today, we'll be presenting the second installment of our industrial cooling series. As mentioned in the previous episode, industrial cooling plays a very big role when looking for energy savings in a factory, mainly because it's rarely looked at and often poorly understood. In part two, we're going to do some more work with cooling towers, in addition to discussing floating heads, seasonal issues, absorption chillers, and a few other related topics. The main purpose of a chiller is to take energy out of either a process or living space. However, all that stuff that's brought into your chilled water system has to be dumped out somewhere. Generally, you're going to have to get rid of 4 to 5 times the amount of energy that was put into your chiller compressor. And all that energy needs to be dumped into the outside world. To do this, we have two major strategies. In one case, you have air-cooled chillers. Think something similar to a car radiator, attached to the top of the chiller normally, and often when the chiller is housed outside. You stick a radiator up on top of the chiller and have a fan on the radiator to remove your energy. Although this is common in certain scenarios, most chillers you're going to see in industrial settings use the second major strategy, where chillers are water cooled with a secondary loop, as shown in this picture, moving energy from the chiller condenser to a cooling tower. Air-cooled chillers or dry cooling towers have the distinct advantage of having no direct contact between water and the air. So the water stays very clean and you're not going to have to worry about anything unwanted entering your plant. You simply bring in water through a radiator and put it back out again. You can see in the figure that the hot water usually comes in at the top and cold water leaves through the bottom. It's just a regular heat exchanger. Pictured here is a large cogeneration plant on the western side of the New Jersey Turnpike just before you get to the airport. Even if you don't live in New Jersey, if you visited at any time and had to go to the airport to leave, then you probably went by this. What we can see is that next to the actual gas turbines and steam turbines is a very large dry cooling tower. It was the largest of its kind when it was first put in place. The reason a dry cooling tower was installed was because when you have a wet cooling tower where you're using evaporative cooling, the water evaporates and generates warm and very wet air leaving the cooling tower to go into the cold atmosphere, and it often tends to condense. This plant happens to be upwind of the New Jersey Turnpike, meaning that if they had used a wet cooling tower, every morning there would have been a dense fog covering the turnpike with an ensuing carnage due to poor visibility. Of course, this is a very specific case. Most cooling towers you're going to see will be wet because they can take advantage of evaporative cooling. The water in this case is not kept separate from the air, but rather it cascades down something called fill, which promotes evaporation. Here, the air cools the water while also evaporating a portion of it. The cooling tower fill, or packing, should resemble something like this. The goal of the fill is to spread the water out, maximizing its surface area to achieve optimal evaporation. Sometimes they will splash it around a little bit in order to increase mixing if faster evaporation is needed. Fill can be made out of many different materials, but aluminum is the most common. They're also intended to slow the flow down as it travels from the top to the bottom of the cooling tower, which allows for increased heat transfer. An important thing to remember is that the condenser temperature is key. The whole purpose of the cooling tower, whether it's wet or dry, is to lower the condenser temperature. If we look at the figure here, which is your classic vapor compression refrigeration cycle, whether it's a chiller or an air conditioner, the compressor does all the work. It's all that you pay for. It raises the gas to a high pressure, which also means a high temperature, and that high temperature is hotter than the ambient temperature, allowing energy to transfer out of the system. If we're able to lower the temperature needed through the use of evaporative cooling, then we can actually lower the pressure of the compressor, thus saving real money and lowering our costs. Now, why is a wet cooling tower with evaporation the best deal going? It's because evaporation sucks up energy by taking liquid water and turning it into a vapor. And that lowers the temperature below the ambient temperature of the air. That's going to help with the performance of air conditioning and refrigeration systems. As a fun side note, the process is what keeps polar bears cool in zoos. Even if it's a very hot sunny day, the polar bears are still quite happy. Now, you might have wondered at some point why you're getting out of the swimming pool, you feel cooler than the outside air, or how those polar bears stay cool in warm weather. That feeling is what we refer to as the wet bulb temperature. It's the temperature that you achieve or feel through evaporation. This differs from the dry bulb temperature, which is the temperature without any evaporation occurring. As mentioned earlier, evaporation is going to suck energy up due to the phase change, which allows the non-evaporated water to cool below the ambient temperature. The device shown in this picture is called a sling psychrometer. One of the thermometers has a wet bulb on it, and you soak that bulb in some water, and the other thermometer remains dry. Now you measure the temperature by spinning this thing around, and then when you stop, you see a temperature difference between the ambient and what we call the wet bulb temperatures. The goal, as always, is to lower costs, and once we have a cooling tower, we must ask ourselves what energy costs we have added through operating. And there are two main costs to keep in mind. First, you must pump your water out to the cooling tower and back, so there's the cost of operating pumps. Secondly, within the cooling tower itself, where you're raining down the water and you're blowing air up through the water in order to get sensible heat change as well as evaporation, you need rather large fans to move the air. Air is moved through two main ways. The first is a blower. It's pushing. It's a positive flow. And the other is a propeller type, where you're essentially going to put a propeller on the top of the cooling tower and suck air into the system. Turns out that if you're looking at blowers versus propeller systems, the cost of your fans is going to be significantly higher for blowers, and therefore the benefits from making adjustments or doing energy efficiency projects on the fan system become much more relevant. Now, referring back to the pumps for our cooling tower, they do have to do a couple of things. Firstly, they have to raise the water up to the top of the cooling tower, so there's an elevation change. And then they have to push water out through nozzles, and thus there will be a pressure drop through those nozzles. Keep in mind you're working with an incompressible fluid, and because pumps work with incompressible fluids, they're much more energy efficient than on the fan side, actually 4 or 5 times more efficient for that matter. So if you need more pressure for any reason, no problem, just add more pressure. So if you're going to look at adjusting either the fans or the pumps, fan side control is the way to go when we're talking about efficient operations of your cooling tower. Now the question is, how should I control those fans? If it gets cold outside, should I back that fan flow off? Remember that the chiller compressor inside your building has a power requirement that's 10 to 15 times that of the cooling tower. So you should always look to lower the compressor pressure and therefore its energy consumption as a first step toward a more efficient system. Now the question is, as it gets cooler outside and the cooling tower gets lower temperature intakes, what should we do? Now, one option, if possible, is to reduce the compressor pressure and therefore the temperature because it's cooler outside, thus making it easier to get that energy to transfer out. Another option is to reduce the cooling tower airflow, which raises the temperature of the cooling tower while having less expense on the fans. Now, if we can't change that compressor pressure, we'll get no benefit from that lower cooling tower temperature. So instead, we'll just back off the fans in that case. These are the two main options you can explore to benefit from colder ambient temperatures. And this brings us to the idea of controlling the energy to the compressor and floating the head pressure. Head pressure, also known as the condenser pressure, is what's achieved by running the refrigerant through the compressor. Conventional designs of chillers aim to provide for that head or condenser pressure, which is to be maintained at or near the design condition at all times. So internal to the chiller, the pressures and temperatures stay the same and the system is stable through the expansion valve. And this is the standard operating procedure. It doesn't matter what the outdoor temperature is because you're always going to raise the refrigerant to the same condenser pressure and no way to save money. If, on the other hand, we can float that head pressure, not make it so high when it's cooler outside, for example. That's going to save money and increase the efficiency of the chiller. And we're not necessarily talking about tiny amounts of savings. In this chart, we changed the discharge pressure. So instead of going up to 15 bar, we only go up to 10. And we find that we go from a coefficient performance of about 2 to 4, literally doubling the efficiency of the chiller. This is simply taking advantage of it being colder outside and not pressurizing the refrigerant as much as you had in the past when you had higher ambient temperatures. If you have a constant head pressure chiller, in many cases, it is possible to retrofit a floating head onto it. This is a relatively new recommendation for us. Retrofits used to not be done, and the simplicity of installation and functionality of the floating heads has improved. There are two main parts to this upgrade. First, you need to install an adjustable speed drive on your compressor. This allows us to spin the compressor at different speeds and get different head pressures. And the second thing you normally need to do, and this is sort of a simplifying feature, is to install a pressure amplifier before the refrigerant goes into the expansion valve. To summarize, in the condenser, we begin with a gas that's at high pressure. Then we take the energy out of it through heat transfer, and it becomes a liquid. From there, it goes into this expansion valve where the temperature drops. So if you're going to retrofit, you put in a variable speed drive on the compressor, but you also install a pressure amplifier before the expansion valve, which is really a pump, so that when the refrigerant goes into the expansion valve, it's at exactly the same pressure it would have been had the compressor temperature been higher. Now, we are starting to see some of these show up in chiller systems in a variety of factories. The whole idea is that when it's getting colder outside, your cooling tower can return colder temperature back to the chiller. And do we want that or not? Well, it turns out if you can float the head pressure, you always want to operate your cooling tower fully loaded, and therefore the colder the return, the better. And the savings are not trivial. There was a case study performed regarding grocery refrigeration systems, and it concluded that for all the refrigerated space they have in a grocery store, they saved on average about 27% by floating the heads. However, it's important to keep in mind that there's also a regional difference here. You'll have more opportunity to float the heads if you're not on the equator. So we've talked about the floating head and the way of changing the pressure in the chiller because it's colder outside. But if that's not available, another energy efficient measure you can implement is fan side control. Even if it's cold outside and you're able to send cooler water back to the chiller, if the chiller can't reduce its head pressure, it doesn't do you any good or save any energy. So another angle for efficiency is that if the weather is drier or cooler, you can save energy just by backing off the fans themselves. Fans operate on a cube law, meaning the power needed is the cube of the flow rate of the fan. So it changes dramatically. Even slightly slowing down the fan will save you a lot of energy. So you'll very commonly see multi-speed fans on cooling towers, but more popular these days is an adjustable speed drive, which can match load needs and optimize the fan's energy. You always want to keep the temperature coming back from the cooling tower the same. Now, cooling towers tend to exist outside and usually outside the view of management. We find roofs and cooling towers to be places where there's usually maintenance issues. And there can be some pretty ugly things, like what's shown in this picture. The fill here is all moldy, and as the mold gets on there, the heat transfer of the surface greatly decreases, hurting the performance of the cooling tower. We see lots of leakage, damaged fill, broken access doors, and much more. Now, if you're trying to suck through the fill in order to get that evaporation and your access doors are stuck open, when you suck, most of the flow is just going to come through those access doors. So there's a lot of maintenance issues on cooling towers that you can look for. It turns out that the cost of a cooling tower is actually small in comparison to the cost of operating your chillers. So if you need to add a tower or to move a tower to a better location, it's all relatively cheap compared to working your chillers harder. Things to keep in mind while placing your cooling tower are questions such as, is that wet exhaust going out? Where is that wet exhaust going out of my cooling tower? It's hot and wet. So is it going into another cooling tower? Or even worse, is it going into the intake of an air compressor or some place where you're trying to dry? Tower efficiency is also dependent upon the physical placement and orientation of cooling tower cells at the facility. If your cooling tower is being blocked by some wall, it's not going to be as effective as if it were out in the open. Although hard to quantify, you should always keep an eye out for things of this nature. Remember, the noise of the fan can be a problem if you have a roof-mounted cooling tower, but that shouldn't be a deal killer. Just work on making it quiet. Roofs can be great places for cooling towers. If you're in the kind of climate where you get freezing temperatures fairly often, you also have to worry a little bit about icing. Now, that's a good thing since the temperature is down to the point where getting cold enough to form ice. But if this does begin to happen, you'll find your operator will most likely be putting antifreeze into the cooling water. Or in some cases, you operate the towers dry, giving up some of the wet bulb temperature benefits so you don't have to deal with the icing in the first place. As indicated to some extent by this picture of an ice cooling tower, changes in the seasons can affect how you're going to operate chillers or whether you're going to operate them at all. The first thing you should do is determine what kind of seasonal use patterns your industrial facility has for cooling. If it's primarily space cooling, it'll typically be different than process cooling. And sometimes if process cooling is dominant, a chiller operation is not going to change very much in the winter or the summer. And the advent of data centers and large computational areas in plants has also generated year-round cooling needs. Still, many commercial buildings can actually shut off chilled water systems from October to April because they just don't need it. Whatever the pattern, chillers set up to operate in August and meet those maximum demands. And they're still going to be running in January, but they'll be running suboptimally. Sometimes it's cool enough outside in January that running a chiller makes no sense at all. So what about wintertime? Many processes need only modest cooling, typically going to be between, let's say, 55 and 70 degrees Fahrenheit. And that's not all that cold. So on some days, the water temperature produced by a cooling tower could be low enough to satisfy the requirements of the process without having to use the chiller. At those times, the cooling tower could serve the load directly, saving all those costs of operating the chiller itself. We call this free cooling. Paybacks can be quick, usually around 1 to 2 years, but you have to think about how you want to implement it. There's trade-offs with each of these, so we're going to discuss a couple ways of implementing free cooling. One method is called direct free cooling. With direct free cooling, you create a second loop where you bypass the chiller completely and go directly to the cooling tower and then back to the load. The red arrows here are showing the operational flow when it's turned on and the chiller is turned off. When you don't want to operate your free cooling, you close those valves and turn the chiller back on. Although direct free cooling has many advantages, there's one main issue which limits its implementation. This revolves around the fact that the chilled water loop actually goes out to your cooling tower and back. So if you've got a wet cooling tower, this means exposing that chilled water loop to the environment, dirt, frogs, moss, you name it. So if you've got an air-cooled cooling tower, this is not a problem. But you have a wet cooling tower and you can't have them mixed. You have to use a different methodology, and we're going to call this one indirect free cooling. With indirect free cooling, you simply add a heat exchanger, so you're not adding a second loop, but instead you're directing the flow away from the chiller and back into the heat exchanger, which is then going to cool the load. So essentially you have the chiller and you have this heat exchanger and you simply operate either one or the other. In this way, you don't have mixing, so there's none of this contamination. It's not quite as efficient. Your heat exchanger is not going to be all that effective, but it lets you have free cooling without any damage going forward. And of course, when you don't want free cooling, you just turn those valves off. Again, I have noticed with free cooling loops in the plants I see that very few of them are automated. They have to be operated manually by the staff, and this remains a problem because the staff often doesn't remember to do it. So moving toward an automated free cooling system is really something we want to see happen, and an opportunity for the industrial Internet of Things. Moving on, I wanted to discuss the simplest way to implement free cooling. However, it requires you to have low enough temperatures at times throughout the year to take advantage of it. And I'm referring to a process called refrigerant migration. You simply have these valves shown in red And if you reach the point where free cooling makes sense, you turn the chiller off and you open these valves. This allows the refrigerant to migrate between the condenser and the evaporator. So there's internal heat transfer taking place and achieving the savings. Okay. The other trick is that the system is normally available as an accessory from the manufacturer. Although this is an option, it may not achieve quite the efficiency as you would get from some of the other measures. This brings us to our latest major topic in industrial cooling, but one that must be addressed. I'm referring to a different kind of chiller you may run into and the reason why you see it. In this picture, you see a conventional vapor refrigeration cycle where we have a compressor over here, which just consumes all of the energy that you need for getting your chilling done. And that's the expensive part. What makes it so expensive is that we're bringing a vapor into the compressor and we're raising its pressure and hence raising its temperature. As you can imagine, when you're changing the pressure of a gas by, let's say, 10 times, you're going to reduce its size by 10 times. So there's a lot of motion here, and it turns out to be relatively inefficient. Pumps, on the other hand, which pressurize incompressible liquids, are, of course, far more efficient, and that's the idea behind an absorption chiller. With an absorption chiller, what you're going to see is that we'll replace the compressor with a pump, but it's a three-step process. The first step is taking the vapor and getting it to be absorbed into a different liquid. So the vapor is now part of a liquid that we can pressurize with a pump, which is very efficient. After the pump, we now have the high pressure vapor, but it's dissolved into the liquid and we've got to purge it out of there. And how we do that is using heat to push the vapor back out of the liquid. We then end up with a vapor at high pressure and high temperature, which is what you want. Some of the common fluids you'll see are a mixture of ammonia and water or lithium bromide and water. The process can get very complicated when analyzing how it works, but you don't really need to see all the ways it's absorbed and pushed out. You just need to realize it's a three-step process. Absorb the vapor, pressurize the liquid, purge the vapor back out of the pressurized liquid. Is this more efficient? It turns out that pressurizing the liquid is going to use up much less energy than compressing a gas, but the extra cost used to heat the liquid and push out the vapor from the liquid is where the inefficiencies appear. The coefficient of performance for an absorption refrigeration cycle is about 1, whereas normal chillers have a coefficient of performance from, let's say, 3 to 4. Well, let's say we have some waste heat sitting around in your plant, exhaust from a furnace or a boiler or some other process. If you can use waste heat to replace that heating needed to purge the gas out of the liquid, then the absorption chiller becomes far more efficient, and that's why you see them implemented. Now, I want to make 2 more important points. First, when you're looking at industrial cooling, ask yourself, are we cooling only where we need to? There are 3 things you want to check on. First off, if you're cooling an area, make sure that it's efficiently separated from other areas. Second, don't use cooling to control humidity, okay? For example, let's say in a plastic extrusion situation where you have chilled molds, those molds can sweat. There can be condensation on those molds, and what you'll do typically is cool the area around there because it also dehumidifies. Instead, the best way to handle this is to go ahead and dehumidify separately from cooling, and it's a much more efficient process. Finally, if you have hot spots that need cooling, don't go cooling the whole area. You can use something such as a vortex tube, which is a device that uses compressed air that's spun very quickly and creates a very cold stream. This can be used for spot cooling in a process. Let's say you're bending metal and at certain points it's getting hot and you're getting problems with quality. You can use a vortex tube to cool that spot rather than cooling the entire area. Lastly, let's not forget that if you have cold stuff in your plant, you can use it to cool other things. I've seen a couple of ideas which are quite clever, such as one guy who makes chicken nuggets for a famous fast food chain. And they use a snow-like feature, making artificial snow with water, which they would apply to the chicken for quick cooling. But they would then take the rest of the snow, put it in a waste bin, and they'd have to dispose of it and pay for disposal. Now, instead of wasting all that cold and paying to dispose it, dispose of it, they now move the snow to another area of the plant where they allow it to melt and put it down the drain so it cools other products with it as it goes. And a second clever idea that you see in almost all dairies is your classic pasteurization process. You have cold milk running through a heat exchanger on its way to the pasteurization process, and hot milk coming back from the pasteurization process, and it's cooled by the cold milk coming in. So it's possible to make sort of a heat exchanger with processes to avoid having to use your chilled water loop. Now, we've only scraped the surface of industrial cooling, but certainly this is an area of great opportunity in industrial plants, and I encourage you to go in and look at cooling with a new enthusiasm. Again, this is Mike Muller from Rutgers. See you on the next episode of IAC 101. Take care.